Previously, we learned about how to adjust the X-ray image for the best sharpness and a good contrast. We can see good pictures. But now we get these pictures on. Actually, why is bone, muscle, tissue, blood, water all different color on the film? What affects that? To know that, we need to know about attenuation of X-rays. So here we go. Firstly, what is attenuation? That's such a pretty word. We can say that attenuation is the exponential decrease in what? In power, energy, and intensity of a wave. I mean, electromagnetic wave is X-ray, right? So these are still talking about waves. So exponential decrease in power, energy, intensity, amplitude, you want to throw it in there? Sure. Of a wave as it travels through a medium. So travels through a medium. So it's a decrease in energy, no? In other words, it's kind of like mist. Isn't this like friction? Well, yeah, kind of. But this one is due to absorption. So I'm going to make a note here. Why? Due to absorption of energy or due to absorption processes. Let's just call it that. X-ray get absorbed by the body or something happen. Okay, absorption processes. Okay. So in other words, this is similar to your idea of damping. If you remember from the oscillation chapter, the idea of a decrease or energy loss. You have something oscillating, but over time, the amplitude becomes smaller and smaller. You lose energy. Same idea here, except that now it's in X-ray and you call it a fancy name, attenuation. So let's set up a scenario to understand this better. What is attenuation? Let's say I draw a box. This box represents the medium that I am going to shoot my X-ray through. Okay, so like a bone, a tissue, whatever it is, a box. So now you have your incident intensity. Rays are coming in at some kind of intensity. I'm going to call this a incident intensity. X-ray coming with a certain energy intensity, and this is going to be called I naught. The zero is called naught, N-A-U-G-H-T. Then something happened inside there, and then when the X-ray come out, oh, the transmitter intensity is not so big already. So this one, after the X-ray passed through a certain medium, this is what we call the transmitted intensity. Whatever that is lah. Intensity come out at the end. So what happened in between leh? The wave get attenuated. So what happened to the wave? Okay, remember electromagnetic wave is what come in, right? That's your wave coming in. So I'm gonna, can I draw that in here? Sure, let me try draw. Wave come in. But then what happens inside? This thing called attenuation happens. So if your middle is, let's say your wave middle is like this, then your exponential decrease or damping looks something like this. So then your wave maybe start off with a pretty big amplitude, but then it gets smaller and smaller and smaller and smaller and smaller and smaller. Lose energy, lose power, then come out, transmitted. Come out. So this is what we call damping, but now we call it attenuation. This shape of this graph, you notice this damping curve, not damping, this pattern, decrease in amplitude, this is what we call an exponential decrease. Exponential decrease. So if we want to plot a graph of intensity against distance you have traveled in the block, okay, maybe you start from here, you travel a certain distance until here, and we call this x. How would the graph look like? So here's our graph. We're going to label the axis. On the vertical axis, we're going to call this intensity A. We use I lah. Against, let's call this distance x. Maybe a certain meter or millimeter, whatever that is. I call millimeter lah, since body ma. cm or millimeter also can. So your wave come in with what? Initial intensity, we're going to call this I naught. And then exponential decrease, right? It's like bzzz, go down. Okay, so you draw the thing that goes down like this. Go down. This is the exponential curve. What can we know about this thing? Well, a few things we can tell is that once you go further away, your intensity will drop. That's all we can say. And this curve have a very special equation. So the equation of this curve, let's go down a bit, has this equation called let's see, where shall I write this? Right here lah. This is the exponential decrease equation, and this is the intensity at any point. Maybe you come until, let's say you come until here lah. This point, x, is the original intensity times this e. What is this e? This is exponential, it's exponent. E to the power of negative mu x. This is the equation of this graph. And yeah, you might have to use it a little bit, but you have to do ratios for this thing. So you have to do ratios with exponents. So what is all this? Oh my, okay. So we're gonna break down this equation and look more carefully of what is this thing. Quick note, this equation applies for parallel beams or almost parallel beam if can. Collimated parallel beam, so the ray come in like that. Okay, if the ray can spread out, then that one your power is changing, your area is changing, too many things changing. So this equation is for parallel beam. Okay, collimated, nice horizontal ray coming in. Okay, so what does this equation mean? It means that, let's say, the distance, you travel a certain distance, let's say this x. I'm going to call this x half. Why x half? Because once I've traveled this distance away, inside, once the wave gone inside the material already, then the intensity could drop down to 50%. So 50% here means I can say this is half of the original, which is half I naught, which is 50% of the original. Then maybe you travel another same distance, that same amount. Okay, you travel until here. I'm going to call this 2 times of the x half. What would that be? So now your 50% divide by 2 again. Become what? 25%. Wow, so you drop again. This is what we call exponential lor. Here drop, there drop. Okay. Where is my line? There. So this one now become 1 over 4 I naught. This is what we call an exponential decrease. So now drop to 25%. Okay, and you can keep going lah. You half and half and half and half and half until everything is gone. So let's draw some dotted lines to show that this is corresponding to this diagram up here. Like that. Okay, so what is the mu? The mu, this mu Greek letter has a very important thing that we need to know. This mu is what we call the linear absorption. Linear because parallel beam, so linear absorption coefficient. This is why we go such pains to make sure the beam is parallel. It will be very complicated. Linear absorption coefficient, or you can say the attenuation coefficient. That's the name for it. So whenever you see these words are absorption coefficient, attenuation coefficient, you are talking about the mu symbol. This one. Mu, the intensity drop down. Okay, so different parts of the body, you can imagine, do you think they all have the same mu as the X-ray pass through? No leh. That's how you tell from different parts. You measure the intensity coming through, and you can tell, this is the picture I'm looking for. You can tell what is the thing that you just passed through. So these are all your mu values. Each part of the body have mu. Which one got the highest? You look and see. Highest mu. Ooh, do you see the biggest value? Bone. So this one has the highest absorption or attenuation coefficient. Which one is the lowest? Air. Hiya, air you don't even see on the X-ray film. Okay lah, air is the lowest. Lowest mu. So on a film, very few X-rays can go through the bone and reach the other side. But in air, everybody just fly through only lah, okay? So that's the mu that you can draw here. So if you want to draw so if you're wondering like, how the graph will change if got different mu, well, you think about it. This mu is what? In the equation, mu is this e to the power of negative mu. How does that affect the graph that we see here? Let's say this graph here is a bone. I mean, a bone. You just send an electromagnetic wave through a bone. So you have that kind of shape going down. What if you change it to something with a less mu, like maybe, what's the other thing? Fat. Let's change to fat. Or water lah, water. Okay, we change to water. Now I send the beam through water. How will this graph change? First, you can think of it. Through water, you don't lose energy so quickly like this. So your decrease in intensity shouldn't be so steep. So your mu will look like this. Yeah. It should it will eventually go down towards the x-axis lah. But my drawing is a bit cha-cha. So let's label this if this is water or anything that has a lesser or smaller mu. Let's call it smaller mu. Mu value. Smaller mu will affect this graph. If you study the graph of exponential in maths, please apply your knowledge. How does this negative mu, this constant mu, affect the shape of the graph? Go check out your graphs. Anyway, bone have very large mu. So we have this thing here, mu, go down. Okay, so remember, bone will cause a lot of energy loss when the X-ray pass through. Loss energy go out. Water, most of the X-ray can still pass through with not too much problem. Okay, so the first thing you need to know, very importantly, is this mu that will keep on appearing in all your past years. And usually they will give you the value. I'm not sure, let's write it down too. So the value they'll give you in the table. And the units, by the way, is per cm or in millimeters per mm. It's just a coefficient lah. Okay, a constant for this mu. Okay, so larger absorption, the bone here, larger mu, lesser absorption, smaller mu. Because after all, this is called the absorption coefficient. So if you have very large mu, you have very large absorption over here. Now, the other thing I want to highlight before I wrap up this section is this x half. What is x half? Look at the graph again. How do we come up with x half? X half is how far you can travel, okay, a certain distance x, before your intensity will drop from original to 50%. So I'm going to put a highlight here. Hey, x half is how far you can travel before you drop to 50%. There is a very fancy name for it. So I'm going to name it down here. The x half, which is half value, half of the value thickness. Thickness, there we go. So this one is the other thing that they will also ask you once in a while to do in past years. How do you find the thickness, how far it go? Is there an equation for it? Kind of, but we need to know how to derive it lah. So you see, if you have this chunk of whatever that is here, bone lah, metal lah, and then you send X-ray in, how far will this X-ray go? How many cm or mm before the amplitude or intensity or power will drop down to half of its original? Well, we're looking at intensity lah, okay? How far before intensity drop to 50%? So we have to do some little bit of equation here. So to find the half value thickness, I'm going to put here, sometimes we call it the HVT. I don't know why they call it that. I guess it's just the acronym of half value thickness. So how do we find that? Question mark. There is an equation for it. Let's derive it together. So firstly, we know that we have this equation up here. This I intensity equation, I equals to I naught, the original, times E negative mu x. So we're going to rewrite that, but in terms of a fraction, I over I naught equals to E negative mu x. Now, at half value thickness, what is the fraction of I over I naught? Means the current intensity over the original. Half Okay, so this means you have already dropped by 50%. So this ratio of I over the original is half. Okay, so this one is half. We can write that down there. So this will be equal to E negative mu x. How do we get the x? This is x half, by the way. That is the half value thickness. We want the x half. But how do we get it out? It's stuck inside the exponent. So we have to do this thing called log and ln. So we need to get the x out. So this is similar to what you do in practical paper 5. We need to take out the thing. So first that I'm going to take the ln, the natural log of both sides. So ln half and ln of e to the power of negative mu x. Now this one got very nice magic because when you take a log inside the bracket, if there are any powers, you can take it out like this. So x half times the natural log of E. And this is ln of half. The nice thing about ln of E is that this thing, you press calculator, what's the natural log of E? Become 1. So it's gone. Bye-bye. Okay, very nice. So all we have now is just x, I'm going to rewrite this, x, which is the half value thickness, equals to negative ln 1 over 2 divided by mu, which is the loss, how quickly you lose energy in passing through a medium. But got negative sign here. Okay, so another way to write this is we want to give a negative sign. Negative of a ln number, you can reverse the fraction inside. So instead of 1 over 2, it becomes 2. Why does that work? Oh, there's some ln magic there that we can do. So this is how we can calculate the half value thickness if we know the mu of a certain object. How far will your X-ray travel before it drops down to 50%? So you can adjust your setting law, contrast, intensity, everything to make sure you have this in mind when you are trying to scan somebody. You want to scan the backbone, but your ray also cannot really reach the backbone, then how? Okay, so remember all these things, okay? So that is the idea of attenuation. Basically like damping, energy loss, or the proper terms in X-ray is absorption. The orange curve, low absorption. Smaller mu means low absorption or attenuation. Whereas the bone, wow, a lot of X-ray lose energy when they go through the bone. So this one is large absorption, large mu. So the computer is very clever one. It will measure all these, computer, actually the film you can see, whatever X-rays make it through, it will cause a different shades of color. So maybe like this one here. This one is HU, but you can replace this with mu lah. It's a different unit. But you can replace this column with mu. Then you set a certain value. Okay, I want this mu to be grey color. So you adjust the machine. Wow, 256 shades of grey. Interesting. Okay. So you set water as grey. Then everything else that is a different mu can be either white or either black above or below water. So it's up to you to what you want to set as grey color lah, to adjust accordingly to have the best contrast to see what you want to see. But the first place why you have different mu is because you have different parts and different linear absorption coefficient or attenuation coefficient. Okay, so a very quick recap of this equation. I'm going to label this now in case some of us don't remember what is this already. So I here is the intensity of the X-ray at any point, any position. This I naught, this one is the initial intensity when it enters the medium. E is an exponent, it's a certain number. Mu represents this decrease in energy, and this is our attenuation coefficient or absorption coefficient. And lastly, the X here is just how far you travel inside the object, distance. cm, units, whatever you want to call that. Right, so that is the idea of this thing. And remember, this only can work for parallel beam. The condition is only parallel beam, because for parallel beam, the area of the beam does not change. Like this one. So we have parallel beam coming in. This is very collimated and nice. Okay, we try to adjust the anode, everything, the setting we talked about before to make sure it's nice and parallel. Because if you have something that is spreading out too much, your equation will not be quite right. Because here, your area is changing. So your intensity is also changing, because intensity is power per unit area. So in the first one, your area, this one, area is same throughout the beam, or almost the same. But if your beam is spreading out too much, this area keep changing. So we don't want this. We only parallel beam, we use this. So we try our best to get parallel beams. Alright, so that's all for this attenuation idea. Hopefully that was helpful in helping you understand how X-ray beams travel through objects, human body, metal, wall, plastic, bone, anything you want to scan, luggage, metal. And remember, it's an exponential decrease as you go through an object, pretty much like damping of an oscillation kind of thing. But now electromagnetic wave already lah. Alright, so that's all for this video. I will see you in the next one. We'll look at some examples on how to do calculation related problems for attenuation in the body. Right, that's all for this video. I will see you in the next one.